Hi, it's time for another math easy solution to discuss integrals and antiderivatives and basically do a useful example that I found in my calculus book that basically illustrates how integrals are the antiderivatives of whatever function you're integrating here. And this one, this one's just a useful example, but it's also in later videos I'll show the exact proof for this, but this is just to allude to my later videos on integral calculus and using antiderivatives and whatnot. So basically, if we look at this example here from integral of from 1 to x of 2t plus 1 dt here, and this value is going to be, well, this one is greater than or equal to 1, just so that this is positive. And then the example states basically determine the area under the curve as a function of x, i.e. a of x here. Okay, so now we know that the integral is just the area under the curve, so then we could just draw this curve out and then basically sum up the area under it from 1 to x here. So now this y, let's say y is equal to 2t plus 1 here. So then this is just an equation of a line here. So when you have y when you put in t is equal to 0 here, you're just going to get y is 1. So we'll just write that down here. This is going to be 1 here. And then at x or t is equal to 1, you're going to get 2 plus 1 here. So it's going to be 3. So we'll just go here at y, we'll just change the scale up a bit, so this will be 2, 3, yeah, so it looks something like this here. So this is our line, so yeah, just assume this is a straight line here, so up to 1, and we'll just call this random side here, or just to pick a random point, we'll call this x here. So now with the area under the curve, we just basic geometry here, and just summing up areas of these shapes here. This is a rectangle, this is a triangle here. And at this point here, if this is y, so that's y of t here, this point here is just going to be equal to y of x. And this y of x is equal to 2x plus 1. And then this point here is just y of 1, and that's just equal to 3. And now this length, or this width of this rectangle and the triangle base is just x minus 1. And this height is going to be 3 here. And then this height here of the triangle is just going to be y of x minus minus this 3 here, and this equals 2, basically 2x plus 1 minus 3, and this equals to 2x minus 2. Just subtract that out. So now we just find the area of the integral. The integral is equal to the area under the curve. Yeah, so yeah, this integral is equal to this area under the curve as a function of x here, and this would equal to the area of this triangle, which is base times height divided by 2. You can see the proof of this in video link below. So this is just going to be the height is going to be 2x minus 2 multiplied by the base, which is x minus 1, and then divided by 2. And then we add here plus, we'll just write it down here. Or just write it here. So basically this rectangle is going to be 3 times x minus 1. So we'll go 3x minus 1. So now let's just simplify it, write it a bit neater over here. We'll divide the 2's out. We're going to get now x minus 1 times x minus 1. And then expand this out, 3x minus 3 here. Now we could FOIL this out, multiplying this by this, adding it to this times this. You can see the proof for foiling in the video link below. This one would just be equal to, well, x squared minus 2x plus 1. And then this one right here is going to be plus 3x minus 3. And then if we simplify by adding the like terms, in this case 2x, negative 2x plus 3x is going to be x, so we get x squared plus x, and then this plus 1 minus 3 is equal to negative 2 here. So this is our area function. That's our integral as a function of it. Okay, so now this brings us to the, part 2 of the example in the calculus book. It would just say, so take the derivative of this area function that we just derived here. So this area function in terms of x, this one is just going to be equal to, yeah, well, the derivative of this x squared is going to be equal to 2x using power rule, and then this one here of x is going to be 1 here. So this is our area function here, and as you can see, this is the exact same thing as our function here. This is actually y of x here. So if we scroll up, so yeah, so this is our function here, but with an x inside because we're using x there. So this y equals 2 plus t, or this one here. So this, as you can see from this, since its derivative is equal to this one, this is an antiderivative of y of x. Yeah, so we'll call this a of x equals to capital F of x when it's the antiderivative of y of x here, because if you take the derivative of it, it's equal to that. So this is the antiderivative of it. So this is actually, it's not just for this example here, it's actually true for all cases, but I just wanted to illustrate it through this example here. So now what this means is, when you take the antiderivative, so yeah, the antiderivative of any function is the integral of it. But in this case here, now you have this -2 here, because we have to subtract from the antiderivative of the 1 here. So in fact, this -2 is actually just equal to, well, we'll call this antiderivative at 1. If the antiderivative of the general is equal to, yeah, we'll just write this f of x first. The antiderivative is in general is equal to, well, this one is going to be x squared plus 1, no, plus x here. Then we have a plus constant here, but we'll ignore it because we're going to be subtracting the same function, but with the same constant. So now in this case here, this is for this one here. So this, if we added the 1 here initially, so we're just going to have 1 plus 1 is equal to 2. So then the area function is just equal to, well, the antiderivative at x minus the antiderivative at 1. Because this one is -2 here, so that's all we have here. So we have this x squared plus x minus 2 here. And this is actually true for all functions, which I'll prove this in my later videos. Well, let's just illustrate this with another example. Okay, so now this example, basically, we'll just, instead of x, we'll find it for 3 here. So basically, solve this. And just I want to illustrate that this is always true here. So we'll just, so this one, if we write it down as the antiderivative at 3, just call this f of 3 minus f of 1. And then I'll solve this using just the area under the curve method like above. And we'll get the same thing here. So if this is this function here, we're going to get now this f of 3. This is going to be 3 squared plus 3 minus f of 1, this is going to be 1 squared plus 1. Because we know the antiderivative is just going to be, well, t squared plus t, or x squared plus x here. So this one's going to equal to 9 plus 3 minus 2. So this is a 12 minus 2 is equals to 10 here. So that's the area under the curve. That's according to this antiderivative method. Now let's just use the graph. Yeah, so if we graph this line out again, but now from 1 up to 3, remember this y is equal to 2t plus 1. So if we put in a 3 in here, so y of 3 is going to be equal to 2 times 3, which is 6 plus 1, so 7. So we'll just write this down here. So this value here is going to be, this height is 7 here. We'll just go write y is equal to 7. And that it's above this axis here. But basically, so we'll have that. Now we'll just find the area of the triangle and the rectangle. This is going to be, well, this length here is 3 minus 1 is equal to 2. This height here, this one, we know that this is just 3 here from the earlier. Just put in a 1 here. So we have 3. So this height is 3. This is 7 minus 3. This height is going to be, we'll just write this down. Well, this is an arrow for that. This is going to be 4. Yeah, so now we just find the area. The area is going to be equal to 3 base times, the width times length is 3 times 2, plus now this area of this one here, 4 times base divided by 2. This equals to 6 plus 4. This 2 is cancelled. This equals 10. Yeah, so then basically the area is this antiderivative, the same thing here. So yeah, this is all I really want to illustrate here. I'll show this in later videos, the exact proof for this in the fundamental theorem of calculus, or the part 1, which is just the integral is the antiderivative. Well, that's all for today. Hopefully you learned from this and learned that the area under the curve is the antiderivative, well, the difference in antiderivatives minus, because it depends on your points here. So you have the antiderivative of the top point minus the initial one here, which, where's that? Yeah, like this one here. So in this case, we're going to have f of 3 minus f of 1. Well, that's all for if you learned, and yeah, stay tuned for another math easy solution.